My name is KylerFillerup, and I'm going to talk about acoustic echo cancellation and double talk detection. This is my milestone 1 video. My faculty advisor is Dr. Farhang. I'm part of the Sorensen Communications Clinic, and my Sorensen advisor is Brett Giles. Sorensen Communications offer video conferencing for the deaf and hard of hearing. And so oftentimes the hearing impaired want to make a call to order a pizza or call their bank. And what Sorensen offers is an ability for them to call into Sorensen, speak to an interpreter who then calls the pizza place or the bank for them. But oftentimes people who are hearing impaired still have the capabilities of hearing some signals or hearing some sounds, and oftentimes they can still communicate verbally and want to do this over this video conferencing system. So in order to do that, the video conferencing system needs to offer pristine audio. The following block diagram details a typical teleconferencing setup where we have two people who are trying to talk to each other. When one person talks, the signal is picked up by the microphone and then played out by the speakers at the other end of the conferencing link. And on that end, the signal bounces around the room and is filtered by the room response and picked up by the microphone. Then that signal is played back by the original speaker, and what they hear is a copy of their own voice filtered by the room, which translates to some acoustic echoes. So these effects can be mitigated by the introduction of a echo canceller. And what the echo canceller does is removes those echoes that are being picked up by the microphone. The entire system can be modeled by the following block diagram, where X of n is the input signal, H of n is the room response, H hat of n is the response of the adaptive system, Y hat of n is the output of the adaptive system, D of n is the signal at the mic, and E of n is the output error signal. Typically we want E of n to go to 0 because in those cases the coefficients of the adaptive system match the room response, and therefore the echoes are completely eliminated. One classical way of approaching this problem is through the use of the least mean square algorithm. What the LMS algorithm is basically an adaptive filter or an FIR filter whose coefficients are updated adaptively. The coefficients or the filter tap weights W of n are updated by the following equation. The next value of the tap weight, W of n plus 1, is equal to the current value of the tap weight plus 2 times mu, which is a step size parameter, times x tilde of n, which is your input signal, times E of n, which is the error signal. Looping through iterations of this algorithm allow the tap weights to be adjusted such that the error is minimized. So the normalized least mean squared algorithm is very similar to the least mean squared algorithm, with the difference lying in the tap update equation. So here we can see that x tilde of n is the input signal, which is taken to be the same size as the room response. So it's a chunk of x of n, which is the same size as the room response, or the number of taps within the room, or the size of W. Y hat of n is the output of the adaptive system, and that is calculated as W of n transposed times x tilde of n. So it's the tap weights transposed, since it's a vector, times x tilde of n. D of n is taken as x of n convoluted with h of n plus some noise. So essentially it's x of n filtered by the room response. And E of n is equal to D of n minus Y hat of n, where D of n is the signal picked up by the mic and Y hat of n is the output of the adaptive system. And the update equation is calculated as is very similar to the LMS equation, except for now the step size parameter is divided by the transpose of x tilde times itself plus a small factor psi, which helps to avoid divide by zero situations when x tilde of n goes to 0. The effect of this is that the step size mu is normalized with respect to the input power. So this is really useful in situations where we're using speech signals because power levels in speech signals fluctuate dramatically. So for my implementation of the LMS algorithm, I focused on two different implementations. First, I focused on the traditional NLMS algorithm as detailed here. And then a second implementation which focused on using the high in frequency, low content of the input signal and applying that NLMS algorithm to those individually. So first, let's take a look at the traditional NLMS implementation. Here we can see a plot generated by MATLAB which details the room response. So basically it's just a decaying random signal, which is typical of a room where a signal will come in, bounce around, and the power will decay as it gets reflected back and forth throughout the room and then picked up by the mic. So here we can see the results of the first implementation of the NLMS algorithm, where the gray signal is the signal at the mic and the orange signal is the error. As you can see, the error minimizes as time goes on. So the algorithm converges to an optimal tap adjustment. So the taps of the adaptive filter adjust optimally over time to minimize the echoes. The echo return loss enhancement is a way to measure the performance of an adaptive algorithm. Essentially, we want the value of the echo return loss enhancement to be as large as possible. And in these cases, ideally if it was infinity, then the adaptive filter coefficients would match the room response perfectly. Here we see we're around a mean value of around 30 something dB. So for the second implementation of the NLMS algorithm, we focus on the spectral content of the input signal. As you can see, most speech signals have a concentration of frequency content at low frequency. So we can take advantage of this fact by splitting up the work of the NLMS algorithm into high frequency components and low frequency components. This is done by the following block diagram. Here we delay the input signal by one sample and either subtract it to itself or add it to itself. Those generate the subsequent signals x1 of n and x2 of n. Then we just apply the normalized least mean squared algorithm to x1 of n and x2 of n respectively, add the results, and we get the desired output error signal. So basically what delaying the signal by one sample and subtracting it from itself accomplishes is it acts as a high pass filter, and delaying the signal by one sample and adding it to itself acts as a low pass filter. So we can see the results of the implementation of this algorithm. We can see that we get a slightly better convergence time. It's not a huge improvement, but it is a little bit of an improvement. The echo return loss enhancement also shows signs of an improvement. It's not, again, a giant improvement, but it is like 1 or 2 dB. So here's a summary of the different algorithms. We can see that the first algorithm presented converges in around 5 seconds and has an echo return loss enhancement average of 34.27 dB. And the second algorithm is slightly better with a convergence time of 4 seconds and a echo return loss enhancement average of 35.1 dB. So let's take a look at the code and how we implemented this in MATLAB. Here we can see first we load the speech signal, then we create our room response. So n is the length of the room, or the number of taps, or the number of W's you will have. And we take that and we loop through each value of n. N naught is just a step to create your random response. We normalize the room response and then filter it with, down here on this line, we filter it with the input signal. That creates our D of n, or the signal at the mic. So for the first adaptive NLMS implementation, we can see first we initialize all of the filter weights to 0. Then we take a portion of the input signal. So x tilde of n is a portion of the input signal, which is the size of w, or the vector w. Then we calculate y hat by taking the transpose of w and multiplying it by x tilde. Then we calculate the error signal by taking d of n, which is the signal at the mic, which is the room response filtered with x of n, and subtract y hat from that. And now we have all the pieces we need to calculate the updated filter taps. And this is done by the following equation. See, we have the current, or the next value of w is equal to the current value plus the step size parameter mu divided by x tilde transpose times x tilde plus a small factor psi multiplied by x tilde and multiplied by the total error. Here we've chosen mu to be 0.5. The larger the value of mu, the faster your convergence. However, you have more misadjustment, meaning that your steps, if your step size is too large, you'll get closer to your value faster, but you'll jump every time you iterate, you'll step over your desired value. Instead of going smaller steps, if you choose mu to be small, you increment by smaller steps, which allows you to approach your desired value more accurately. However, it is slower. So here we can take a look at the second implementation of the NLMS algorithm. And in this implementation, we implemented the room response the same way. And however, the difference here is we have two vectors for w. Here we kept mu the same 0.5 so we can compare the results. We still take a portion x tilde, which is the same size as w. In this case, it's 2 times w, since we have twice as many. Then we take x tilde. 1 is equal to x tilde delayed by 1 plus itself. And then we have x tilde of 2, which is x tilde of 2, which is a portion of x tilde here, delayed by 1 minus itself. So we delay x tilde by 1 and add it to itself, and we delay x tilde by 1 and subtract it from itself, yielding x tilde 1 and x tilde 2. Then we multiply x tilde 1 by w1 transpose, and we add that to w2 transpose by x tilde of 2, and this gives us our new y hat. Then we can calculate the error signal, which is d of n minus y hat. So if you notice, the error is the total y hat. We use the total y hat to calculate the error. We subtract y hat, the total y hat, from d of n to calculate the error. And then we have w. We update each tap vector independently. So we have w1 plus mu, and here we have x tilde of 1 for w1. We go back up here. We have x tilde 1 for w1, and here we have x tilde 2 for w2. And then if we continue to scroll down, we have the echo return loss enhancement calculation and the plots. So for my milestone 1, I was supposed to learn about adaptive systems and adaptive filters, implement a least mean squared algorithm, understand and implement a normalized least mean squared algorithm in MATLAB, and simulate the results. And here are my results. Thank you.